Hello, everyone. I'm a PhD student from Technical University of Munich. Frank Pohlmann is my supervisor, and I'm going to talk about a side project that's mainly done last year. And I'm very happy to have this opportunity to kind of talk about this ongoing work, which is not complete. And I was taught that this is about a NetKit related talks. So I kind of would be more elementary and kind of involve more technical details. And I hope the practitioners could pick up something especially related to this neural autoregressive quantum states approach. And mainly today I'm going to talk about the particle number conservations symmetries over here. Okay, so a slight kind of motivations. Of course, we heard a lot of nice talk from Huang and Pan Zhang about this approach of autoregressive models, but share just another motivations about it. So we know that it's hard to simulate 2D quantum system, especially for open boundary conditions and also open like finite systems over here. So the state-of-the-art results will be PEPS simulations. And here it's plotted with respect to a number of parameters and the relative error over here. And we see that the neural autoregressive quantum states gets even lower error rate comparing to the PEPS results. And even more surprisingly is that, so to get this kind of accuracy PEPS results, one need to kind of start with a cheap, simple updates approach and then kind of include like enormous computational hours, say more than 10,000 CPU hours to get down using a gradient descent approach to here accuracy. And then one can kind of argue that neural autoregressive quantum state is more efficient because this only requires, say, a few hundreds GPU hours. And so we heard a lot of talk about kind of parameterizing quantum states with neural network. In general, this kind of approach, there's no limitation on the form of the neural network one considers. One simply then take Markov-Chain Monte Carlo to generate the samples. Then you can study your kind of favorite problem, ground state search or tomography or even dynamics. The problems about this approach is that the wave function is usually not normalized and there might be some numerical instability. And a more important problem is that Markov-Chain Monte Carlo, sometimes it's hard to get the correct statistic because of long autocorrelation time. This two problems is especially severe when one go to deep neural network. So for example, if one simply plug in a ResNet with say 20 layers to simulate some wave functions, it would basically not work because of the sampling you get is probably not the correct statistic and you can easily get exploded wave function somehow. And also Kenny mentioned some sampling problem when he's working on quantum chemistry. It's basically also related to this problem. So the approach, kind of the solutions one kind of proposed from O'Sharir and his collaborator, also Giuseppe Collier, last year is to use this neural autoregressive quantum states. So I just want to give a big picture first. So it's kind of an autoregressive model. So the basic idea is that one can always represent the joint probability distributions by a set of, by the multiplications of conditional probabilities. One can simply do that to the probability amplitudes and kind of take the multiplication of probability, conditional probability amplitudes. It's kind of already considered in the 70s, but it's more only come back in these 2 years. And there's also exponential scalings in expression in this form. Then one simply just said that, okay, now we approximate this conditional probability or conditional probability amplitude by the neural networks. Okay, this is the big pictures. And now I'm going to a little bit detail right now. So what's the advantage of working with this format is that you can do kind of exact samplings. So you can kind of first sample from the P of X1, because this is the exact marginalizations. Then once you have X1, you plug into the conditional probability over here and sample X2. Once you have X1, X2, you sample X3. Then you kind of do this sequentially and exact unbiased sampling. The most important thing is that all after the sequential sampling, you get independent samples. So you do not need to throw away a lot of the samples that you have, but each sample is independent. And to overcome this kind of exponential scaling to keep the full conditional probability, again, one just do some approximations. So the simplest approach would just say drop some dependency, or one can also approximate this with other functions with less parameters. So a simple approach over here is say that, for example, if we have 4 variables, we know, and if we have some prior knowledge about the system, we can just say we throw away some dependencies. Say we know that x4 does not depend on x1 and x2, we just throw it away. Also throw away here. Then we can write down the simpler models over here. This is the so-called graphical models. And one can generalize this kind of approach to probability amplitudes. Then one just get something similar to entanglement blockhead states, or correlator product states. The other approach or example would be that, okay, so we approximate this conditional probability by another functions, which would be simpler right here. So kind of a familiar approach would be using a unitary tensor network. So say if the probability distribution or the probability distribution that we're considering is coming from a Bohr machine, or say MPS. And if you put the MPS in the right canonical form, then you can have, like, for the reduced density matrix for the first spins, you can sample it exactly. You plug in into here and you can sample for the second spins. You can do it so on and so forth. This is also known in the tensor network community, but probably not in the language of autoregressive model, but you can kind of think of it this way. And then, so another definitely common here is that you can do it with neural network. So we want to approximate the conditional probability of x2 conditional x1 by, say, a function of g2. P of conditional probability of x3 on x1, x2 by a function of g3, so on and so forth. So basically what I meant is that we want to set the output of the neurons to be the conditional probabilities. And then to do this, we see immediately that we have to have some restriction in the structure of the connectivity, because say G2, if we want to be a probability, conditional probability, it should only depend on X1. If G3 want to be a conditional probability, it should only depend on X1 and X2. So basically the idea is simply that we have a type B operations, which kind of depends only on the neuron to the left and to the one below. And then type A operation, which depends to the neurons to the left. By ensuring this kind of connectivity, one ensures the causalities. And after that, you just need to normalize the output neurons to get the normalized conditional probabilities. So at this point, it's quite simple. Then you have a normalized conditional probability and you can parameterize the joint probability distributions. Can do it with deep neural network as you wish. Can do it with conditional probability amplitudes. You can generate kind of real image by doing this approach. Then we're all ready to go with the probability amplitudes approach. You just simply replace the probability with probability amplitude, the conditional probability with conditional probability amplitudes. The only thing might change is the normalization condition over here, that we're now taking a square instead of simply just summing over it. Okay, and then the sampling is quite straightforward. You sample from the first side 1 here. Once you get the spin 1, you compute the conditional probability on S2. Notice that we always need only computing kind of half of the neural network over here. Then you plug it back in, you sample for the spin 3. You do this sequential approach, and then you get the full kind of configurations and also the probability amplitudes. Again, you can apply similar methods to study ground state and others, tomography and other stuff. And then, so the question I want to answer over here is that how do one sample for a state with fixed number of particles? There's some problems with naive projection, because if you do naive projection, you lose the normalization that we have. And especially if, say, we are kind of optimizing towards the ground states and you want to target, say, the first excited states, then you might, if you do the naive projection, you throw away lots of the samplings that you have. So the solution is just one, do the projection at each step before the normalizations. So example over here is that if we want to sample 2 up spin and 2 down spins over here. We sample the first side, we get an up spin. We sample the second side, we get an up spin again. And if we sample for the third side, we get a down spin, then that's fine. But if we kind of get the up spins, we should say, no, stop here. This is not allowed. And how do we do this? Is just I would kind of add a bias to our neural network to kind of project or select out the configuration that is now allowed. So the answer is that we first need to know like what kind of configuration should be allowed in our samplings. So this is kind of a general framework that to target certain particle numbers. This also applies to bosons, not only to spins. So we kind of consider this sequential sampling process as a walk on the grid. And we start from site 0 to site n. And then we want to end up in the targeted kind of number of particle we want, for example. And for example, in this case, we consider that at each site, you can at most fill in most 2 particle. So you will say, okay, I go to for site 1. At most, I can fill in 0 particle, 1 particle, or at most 2 particles. We can go on like this to somewhere over here, but we add a cutoff in front, on top, because we know that we should not allow more than the particle we want. And then you also need to count it backward. So if you want to fill in, say, 9 particle in this case, at the one side before the end, you know that you should at least have 7 particles. Otherwise, you cannot fill it into 9 particles. And you can count it backward like this. Then these points in the middle are the points that's allowed. So basically, this is kind of a linear constraint, and one can add it as a single layer neural network over here. The important thing is that this kind of satisfy the same connectivity constraint that I set. So they basically satisfy causality structures. So we can simply implement this inside the neural autoregressive quantum states framework. And as a proof of principle, just very simple examples, we can kind of look at Heisenberg models. We first run gradient descent to obtain the ground states, then almost ground state, like you get pretty nice accuracy over here. Then you switch on the particle number conservations. So you can say the total spin SZ equals 0 and total spin SZ equals 1. And you optimize, for example, this one, then you got the excited states over here. And we know that it's a gapless system. So if you do a finite size scaling, so you kind of see the gap goes to 0. So almost done with my presentation. There's some comparison with the tensor network. Using this approach, it does not lead to speed up. But you kind of have a flexibility that you can turn on this conservation at any point during your optimizations. At first, I thought this would kind of lead to speed up in convergence, but it's not actually the case. Yeah, but that's kind of quite flexible. So this kind of towards the end of my talk. So this kind of overview about all the classes or like all the talks that we have heard about like recently. So especially I want to mention that this is kind of a direct sampling approach, which is very nice. And one can work with deep neural network, like the one, like what Sharir has done, and also like what I've tried to do down here. We kind of do more than 20 layers and go to very deep neural networks. And one can also kind of, because of the statistics correct, one can go to Rainy and entropy, as like pointed out in this paper. And one can also, so this work basically is talking about the U1 symmetry that one can have. And I hope that once we have this kind of auto differential framework set it up correctly, we could kind of incorporate this neural autoregressive quantum states into a naked framework. Yes. And I have to say that while preparing for this presentation, I realized that like I think this approach is similar to like Juan's approach done in the recurrent neural network. Yeah, I realized that during my preparations.